Welcome to ENGR 221, ENGR 221. The title of this course is Electrical Engineering and Circuits 1. All right, so this is sort of the beginning class of learning about electrical engineering. And what I'd like to do right now is sort of go through the various topics that we're going to cover in this course and talk through them so that you can have an idea of what is coming up in the course, okay? So, one of the things that you'll also notice in Moodle, where we have all of our documents and everything stored, one of the things that you'll notice is that a lot of our topics have these little letter labels on them, okay? And that's kind of an easy way for me to refer to various sort of topic groups that I think of and kind of how this course breaks down into various topical groups, okay? So topical group A really isn't so much course content as it is just sort of orientation materials to the course or kind of the big picture of the course. So I would sort of put this little presentation right here in group A because I'm just talking about general idea of the course. But after this, going from group B and onward, these represent sort of the actual topics that represent, the true content of the course, if you will. Okay, so things that would be included in A might be our syllabus or contact info for me or links to your review materials or in-class assignment mini-lab submission portals. But we're going to move on now into what are the big ideas or the basic ideas of this course, okay? So B here, it says basic ideas and quantities. One of the things I'm going to get to later today is giving you some terminology that goes along with the construction of networks, okay? So I'm going to talk through some of that today. That's sort of really general stuff so that when I use certain terms, when we start getting into the circuit side of things, they have some kind of a meaning that we've already talked through, okay? The other thing that we'll deal with this idea of basic ideas and quantities is what are our most essential electrical quantities. And just to kind of say what they are, we're going to be talking about electrical current, voltage, and power. Those are our most essential electrical quantities that we're going to be dealing with. Once we've talked through that, many people think of the most ubiquitous thing in circuits as sort of being Ohm's law, right? Some of you have seen Ohm's law before, V equals IR, right? So it's a way of sort of relating for a particular circuit element, what is the voltage across that circuit element and what is the current going through that circuit element. It turns out, though, that even Ohm's law can get a little bit more complicated than it looks like at the surface, because Ohm's law, if you don't say something else about it, seems to indicate that you're going to have a constant for that relationship between voltage and current. So I'm going to talk through that a little bit when we get to that day, because there can be some more complicated relationships between how much current flows and how much voltage is across a particular element. Particularly, there can be some ways that becomes nonlinear. In other words, as you increase your voltage, it's not necessarily just proportionally increasing the amount of current. That relationship can be nonlinear for certain types of circuit elements. The other thing that can happen is there can be time-dependent relationships between voltage and current. And we're going to get into a couple of those even in this course. So that's why I've got that as its own sort of topical group, is that establishing what the voltage-current relationship is for a particular element may not be quite as simple as just saying V equals IR. So we'll talk about that a little bit more when we get to that phase. The next thing that we've got is kind of what I think of as being the most central to everything we do in this class, right? They are Kirchhoff's laws, right? Kirchhoff's voltage law and Kirchhoff's current law. The big ideas of those is for the current law, it basically says that all the currents that enter a node had better also leave that node. A node doesn't really have a capacity to somehow just magically get rid of the current that flows into it or to kind of store it up or something like that. Nodes actually, operate kind of on a zero sum, if you will, right? Similarly, for the voltage law, If you add up all the ways that voltage might increase as you go around a loop, those had better balance all the ways that voltages decrease as you go around that same loop, so that you end up at the same voltage where you get to the end of your loop as you were at the beginning of your loop. So these are kind of the two big ideas of Kirchhoff's laws, and Kirchhoff's laws form the foundation for most everything that we're going to be doing in here. So that's why we give that a large amount of attention. There's numerous techniques that come out of Kirchhoff's laws. One of those is kind of a lot of techniques surrounding equivalent resistance. Almost all of you probably took our first freshman series class that we have here, where you did a lot of things surrounding equivalent resistance techniques. One of the reasons we present that at the freshman level is it gives you one of the most powerful tools that you can use with the least amount of overhead. You don't have to understand a whole lot about what you're doing with equivalent resistance techniques in order to solve some fairly, even some fairly complicated problems, okay? But what we're going to do is present that, even the idea of coming up with your equivalent resistance, that even that idea is based in Kirchhoff's laws. And that's how we're going to kind of look at it to begin with this time we go through it, okay? Related to that is ideal source combination, okay? So maybe the best example I can give you of this is that if any of you have kind of opened up a flashlight and you have to put in, let's say, 2 AA batteries into your flashlight, and then you close it back up, and they're usually in a stack, right? Those would be 2 voltage sources. We'll talk about whether or not a battery is really a voltage source as we move along, but those are kind of like 2 voltage sources that you stick in series with one another. Those can be combined together to make a different kind of voltage source, right? Those kinds of combination techniques can be done for both voltage sources as well as for current sources, and we're going to talk about those kind of also in this context of Kirchhoff's laws, okay? The other thing that we can do is there's a couple of really powerful equations that make finding how much current flows in a particular branch of a circuit easy, or how much voltage is dropped on a particular circuit element that's in series with another one. There's a couple of really easy formulas that we can use to do that. We typically call those voltage division or current division formulas. And so those will also be presented in the context of Kirchhoff's laws. So that's coming up. In case you're wondering what these little numbers are over along the right edge, that's approximately the lecture number, the kind of the meeting numbers, maybe what I should say instead. The sort of serial number of times that we get together and do something, that's approximately when those happen over there on the right bar, okay? All right, from there we get into another really big idea, and that is superposition. I have it listed here under E, linearity and superposition. The big concept there is that if you have a linear circuit, you can look at the voltage across a particular element or a group of elements, or the current through a particular element or maybe a group of elements, and you can evaluate what that value is going to be, the voltage or the current, for each source connected to the circuit individually. Like, you can basically pretend like it's just one source at a time connected to the circuit. And then once you come up with, let's say we're dealing with a current, right? Let's say you come up with a current through a particular element caused by one of the sources. And then you come up with a current through that element caused by another source. And you do that for all the sources in the circuit. If you add up all those current values, that will be the total current that will be caused in that element from the combination of all the sources, right? That concept there is called superposition, and it is very similar to superposition principles that are very commonly used in other classes that you've been in as well. This idea of superposition is sort of a transcendent idea that is used in essentially, I won't say all necessarily, but quite a few engineering disciplines use this idea of superposition to deal with different things. All right. After that, we get into these 2 topics here, nodal analysis and mesh analysis, okay? One of the comments I've heard people say when they take this course is once we hit these two concepts of nodal analysis and mesh analysis, they go, why didn't we cover that first? Okay, there's a good reason. We want you to be comfortable with all of the underlying theory that you know, these two ideas are based on, but they are extremely useful techniques to deal with even the most complicated of circuits. Okay. When you use these techniques, it almost always results in you getting a system of equations, right? For most, you know, reasonably sized circuit problems, you almost always end up with a system of equations that you've got to solve. I liked what a friend of mine that, you know, actually I don't even remember who it was that says it, but when I was taking circuits, we finished with our lecture, I believe it was on mesh analysis, and this person that I knew told me as we were leaving, is like, now I feel like we're using KVL to its fullest potential. And he didn't even understand that he just made a cool pun. So I usually relay that to people. We're using Kirchhoff's laws to their fullest potential when we get into nodal analysis and mesh analysis. Those of you who didn't get the joke that I made right there, potential is another word for voltage, right? So that's what the joke is there. All right. After that, we get into another very useful technique that is called source transformation. And what I've got it listed as here is kind of the idea of practical sources, and what we can do is called source transformations. The underlying idea on this concept is that when you have a real voltage source of some kind, earlier I kind of alluded to the idea that maybe a battery wasn't really a voltage source, okay? Even though a battery in a lot of ways acts like a voltage source, it isn't truly one, because a real or kind of an ideal voltage source, when we write one of those up on our page, assumes that it will supply that voltage regardless of how much current it has to also pump out at that voltage, right? Well, those kinds of devices don't really exist in the real world, right? But what we can do is we can construct a real or a practical version of those same things using, in the case of a practical voltage source, you use an ideal voltage source in series with a resistor. Or in the case of a practical current source, you use an ideal current source in parallel with a resistor. And it's possible for us to essentially do transformations between a practical voltage source and a practical current source, and it turns out that becomes a very useful circuit analysis technique to be able to do that transformation. So that's what we're going to cover, and that is, at least in this implementation of this course, going to be the last topic before we hit exam 1. Okay, the practical sources and source transformation topic will be the last one before exam 1. Even though it's the last one before exam 1, you'll notice that with this course, at least in this implementation of it that you guys are taking, we usually space out from the last topic that we're going to cover, usually give it a couple of days or at least a day before we have you do the exam. So that's why I number exam 1 as 12 right here, right? So that's going to happen actually after we get into and cover a little bit of stuff about Norton and Thevenin equivalence, okay? So I won't spend a whole lot of time talking about exam 1. We'll talk about it more when we get there. Let's talk about Thevenin and Norton equivalence. The big idea on Thevenin and Norton equivalence is that even if you have a huge messy circuit written on your page, if you identify a couple of terminals on that circuit, right? Like you kind of say, I'm going to look at this point right here on the circuit and another point on that circuit in another location. Even if it's a big, messy looking circuit, that circuit can be reduced to one of the two practical sources that I was talking about earlier, with either a practical voltage source or a practical current source. This huge, messy circuit can be reduced to an equivalent practical voltage source or practical current source, even if it's big and messy, right? And so those two types of sources are called a Thevenin equivalent in the case of a practical voltage source, or a Norton equivalent in the case of a practical current source. and I'm going to show you some techniques that we can use to get to Thevenin and Norton equivalence. Okay? There's not really that much new presented in that sort of area. We're going to be using all of our circuit analysis techniques we had already learned up to that point in order to find those Thevenin and Norton equivalents. Anyway, it's a pretty neat thing that you can take a big messy circuit and get it reduced down to something that is more manageable. You know, and I guess the theory is useful in that you know that something like that should exist as long as you've got a linear circuit that you're dealing with. Okay, so that's kind of neat. All right, after we get into Thevenin and Norton equivalence, we're going to introduce a couple of circuit elements that we will not have really dealt with up to that point, called inductors and capacitors. Okay, and I've got it written up here kind of more as the phenomenon rather than the circuit element, but I call it inductance and capacitance. So those are kind of these physical phenomena that happen. Inductance is essentially kind of the process of storing energy in a magnetic field. Usually it's around a coil of wire, okay, of some kind. Capacitance is the idea of storing energy in an electric field, and usually that happens whenever you have two conductors that you put close to each other but not connected, right? There's some amount of capacitance that happens due to the electric field that forms around things like that whenever you get two conductors close to each other but not touching. Kind of the idea with these is that because you can store energy in those two modes, it creates different kinds of behavior in circuits. And I do need to say that the amount of energy stored in inductors and capacitors is usually very small relative to the overall amount of energy that might be passing through that circuit. And it's also usually stored for very short periods of time relative to the kind of periods of time we're used to thinking about, right? So if you're talking about minutes or even sometimes even seconds, that might be an eternity with respect to the amount of time that an inductor or capacitor stores a certain amount of energy. All right. The big thing that inductors and capacitors do in circuits is they introduce time-dependent behavior. So instead of it being the kind of thing where you flip on a switch and if you've got just a resistor, let's say, hooked up to a voltage source, you flip on the switch, pretty much instantaneously that circuit reaches the operating state that it is going to be in, pretty much right away. But if you turn on a switch and you've got something like a capacitor and inductor in that circuit, it might take a longer period of time, a finite amount of time, for that circuit to reach sort of its operating state. And that's kind of a good segue into the next little phase of our course, and that is called DC Transient Analysis. The word transient refers to the idea that once there's a change that occurs of some kind in your circuit, it can take a little while for the circuit to reach a new state that's called a steady state, right? So you cause some kind of a change, and there are some behaviors that happen for a limited amount of time until the circuit reaches its new steady state. All right, so we're going to have an analysis of that. When we were dealing with inductors and capacitors, I didn't say this earlier, but in addition to kind of showing you how inductors and capacitors can be built, I'm going to talk about the mathematical models that we use to actually work with them. And it turns out those mathematical models involve integrals and derivatives that are based in time. So that's where the big kind of time dependency that I'm going to talk about when we get into DC transient analysis, that's where that time dependency comes from, is that our mathematical models of those kinds of elements include time. Okay? When we use those descriptions, those mathematical descriptions of how inductors and capacitors work, because they are described in terms of derivatives and integrals that are based in time, what those lead to is they lead to differential equations also based in time. all right? And the solution to those differential equations is how you go about figuring out what a circuit will do when it's got this transient behavior going on. For some of you, this may be good news. Others of you, it may not be. Some of you really love to do math for its own sake. And some of you say math is really just a vehicle to try to get me to a place that I can analyze something I really care about, right? I probably have both camps represented here in the room. If you really love math, you will probably love doing this first order differential equation stuff that I use to show you why it is that we can do the techniques that we do for our DC transient analysis. The others of you will say, I guess I got to get through that so that I know where it came from, but I'd really like to get on to this last bullet down here that says I'm going to show you an easier and more powerful technique to deal with those same circuits, and it won't feel like you're dealing with differential equations when we get to that stage. Does that make sense? So I just wanted to kind of explain where we're going with that. That is the last topic that we're going to do before we hit exam 2. Okay? Or really, I should say it this way, the last topic that is going to have content represented in exam 2, at least this quarter. We are going to then get into this other topic called operational amplifiers. An operational amplifier is something that is important to cover in a basic circuits course because they are such common devices that get used in a lot of different areas. I'll give you a couple of examples. Operational amplifiers can be used in devices that we think of that are just amplifiers. Like let's say you have an audio signal that you want to boost that audio signal somehow. An operational amplifier is sometimes a piece in that process to amplify that signal. An area that you may not have actually seen before, but it's very common in engineering, is a lot of sensors that are out there will produce some very, very small power signal of some kind. Some of you may have seen something like a strain gauge, for instance. Okay? A strain gauge measures how much strain is happening in a particular element. Not to bring too much statics into our circuits class, but that's a device that can do that. But the signal that comes out of a strain gauge does not have a large amount of power capacity. In other words, it can't just automatically cause there to be even a needle that sweeps on a gauge per se, because it doesn't produce power enough to do that kind of thing. Okay? So a lot of times what we need to do is we need to take really, really small signals that might come from various kinds of instrumentation and boost those up to levels that we can actually read them in something like a microcontroller or something like that. Okay? So that's another real big application of operational amplifiers. How we are going to approach those in this class, though, is even though inside of an operational amplifier package, which is like a commercially produced little thing, you know, sometimes they call them a dip package, but it's basically this little thing that almost looks like a little caterpillar. It's got little pins sticking out of it, okay? That has a lot of circuitry built into one of those little pieces, and I'm not going to ask you to understand all the kind of transistor level behavior of a component like that. What I'm going to ask you to do is understand these big mathematical models that are supposed to do a reasonably good job of modeling how that device is supposed to behave. Okay? And we're going to be dealing with this with things that are called ideal op amps. So we're going to assume that the op amps that we work with are capable of behaving ideally, even though later on you may start learning, not in this course, but later on, especially if you're a double E, you'll learn some ways that operational amplifiers may not behave according to their ideal scenario, right? But there's enough applications of them where they do essentially behave close to ideally that it's worthwhile us learning about those rules that we can use to analyze those kinds of circuits. Okay? So that's actually, if I was going to kind of pick out one most important thing to say about operational amplifier circuits, it's that I don't care that you memorize a certain number of circuit recipes that we can do with operational amplifiers. That's not really my point. I think it's valuable for you to see them maybe, but I don't want you to necessarily memorize them. What I want you to do is learn essentially what ends up being two basic rules that you can use to analyze any ideal operational amplifier circuit that might be out there. And that's kind of the big outcome I would like to see happen. All right. That kind of marks a big transition that we're going to do in the course, and you might be able to see that when we get to this next topic. I've got labeled L up here, where we do a review of complex numbers. If you look at kind of the flow of the course, this feels like it comes out of nowhere. We're doing all kinds of circuits analysis stuff, operational amplifiers, and then all of a sudden we hit, what? A review of complex numbers? Here's why we review complex numbers. It turns out that it is possible for us to use all of the same techniques that we developed for our DC circuits. We can use all those same techniques, but analyze circuits where you have alternating current, right? Alternating current is this idea that a lot of the different electricity that we use, including the stuff that comes out of the outlets in your walls at your home, it's not just some flat voltage that's being delivered at some level. It is a sine wave of voltage, okay? When we're dealing with and analyzing those kinds of circuits that have alternating current, without some kind of a tool to use, it would be pretty daunting to try to figure out what happens in those circuits where we've got waves instead of just being some constant value, okay? The good news is we can use complex numbers to set up our problems in such a way as they are solvable using all the exact same techniques that we used for our DC circuits, but we can do them for AC circuits with one change. And that change is that instead of operating on numbers that are entirely real, we operate on numbers that are complex, meaning they have a real component and an imaginary component. All right? Once we got that change in there, the techniques themselves don't really change. Okay? So that's where we go to with the last little couple of bits that I'm going to talk through here. Phasors and impedance is what I've got labeled M right there. A phasor is a quantity where it's got two pieces of information built into it. One of them is an amplitude, and one of them is a phase angle. So when you think of there being waves of electricity, like sinusoidal waves, and you try to think of if we're dealing with steady state waves that's just sort of one frequency at steady state, the two factors that are kind of most important for us to think about are how big is the wave, right? What's the amplitude of the wave? But then the other factor that's important for us to think about is how does that wave line up or not with other waves, right? So that we call that a phase angle. A phasor is essentially a complex number that carries those two pieces of information. What's the amplitude and what's the phase angle, right? And we can represent voltages and we can represent currents with those kinds of numbers. It turns out it's a complex number, right? But it carries those two pieces of information, the amplitude and the phase angle, okay? Simultaneously, it's possible for us to take our passive elements in a circuit. Resistors, we already knew how to deal with resistors, so that's not really what I'm talking about, even though it is a passive element. The other passive elements that are in circuits are inductors and capacitors. Inductors and capacitors can also be represented with things that are called complex impedances. And those complex impedances are essentially complex numbers, but they behave just like resistances when we were dealing with DC circuits, okay? So we can essentially express voltages and currents as phasors, and we can represent our passive elements with these things called complex impedances, and now we have all the pieces that we need in order to be able to represent our AC circuits. Isn't that kind of cool? So that's what we're going to get into when we get into phasors and impedance. I'll mention this right now is when you try to describe the full shape of a wave, it's important that you have time built into that math, right? Once we get to where we start describing a wave instead of with, kind of the full-on shape of the wave, and we only describe it in terms of amplitude and phase angle, we no longer have to have time included in the mathematical representation of that, right? If all we're dealing with is just amplitude and phase angle, time drops out. And so One of the things we're going to talk about when we get to that point is time domain, where we do have time factors in our various expressions, versus frequency domain. Frequency domain essentially allows you to drop time out of your mathematical expressions. So all this whole process of going to these complex numbers, one of the ways that people describe that is by essentially converting to frequency domain. And that allows us to not have to deal with time directly. Does that make sense? All right. I think that's about all I wanted to say on that point. Point N, right, you know, kind of where we get to this AC steady state analysis, it really isn't much different once you get to that point than doing DC analysis. The only difference is you're going to be operating on complex numbers as opposed to operating on fully real numbers. Okay? You just convert your voltages and currents into phasors, and you convert any of your passive elements into impedances, and you know, you're good to go. Everything will sort of work like it did in DC circuits. Now you just have to operate on complex numbers as opposed to real numbers. Last point that I made right there, let's say you're using some kind of a method that you used in DC circuits, and you come up with a system of equations. And back when we were doing DC stuff, you were using your calculator that you're allowed to use, right? You're restricted to using just FE-approved calculators on your exams in the course, right? So you're trying to, you know, punch in a system of equations. If you're doing it in real numbers, your calculator has some really nice tools that will do that and make it very easy for you to solve a system of equations. When you go to complex numbers, that gets more tricky. You can't use the calculator in that way anymore. That's the bad news. The good news is your calculator actually does have a lot of tools built into it that can sort of automate a lot of the arithmetic that you have to do with your complex numbers. It can do things like store complex numbers and do complex arithmetic for you. So those things it can do, it just might not be able to solve a big system of equations. All right, and then we get to our last topic in the course, and that is AC power. So what's interesting about AC power as opposed to DC power is that with DC, there's no wave kind of form that you have to be cognizant of. So if you know the voltage and you know the current, power is just voltage times current, right? DC, it's very, very easy that way. With AC, it's not just how much power or how much voltage do you have and how much current do you have. It's also, do the peaks of the voltage line up with the peaks of the current? Or do they anti-align, right? Or are they offset by some amount in phase angle? There's all kind of possibilities that you can have there, and it bears a lot on how much power is actually transmitted from one element to another in that circuit. You know, kind of that concept of phase angle and amplitude. The phase angle is a big factor when it comes to coming up with how much power actually gets transmitted from one element to another in a circuit. Okay? I'm going to present this concept of a power triangle, because it turns out that in AC circuits, one of the things that can happen is that power can be sent along some wires from one element to another. Let's say the element at the other end of the line is a capacitor. Because it has the ability to store energy, it can send that power to that capacitor. The capacitor can store it for a tiny amount of time, and then it can send it back. And that's what does happen in AC circuits, right? So that amount of power that just sort of goes back and forth from one element to another but doesn't really do anything, that is called reactive power. And the wire does actually literally have to carry that power back and forth between one element and another. It's just that the power is not really doing something physical when it gets there. It's just getting stored for a second and then sent back, right? As opposed to the other kind of power is called active power. And with active power, it's power that gets sent from one place to another and then actually does something when it gets there and it doesn't get sent back, okay? So anyway, the power triangle that I mentioned a second ago is a way to sort of graphically show the relationship between how much power really does something and how much power is just getting sent back and forth in the wire, all right? I mentioned up here a power factor. A power factor is a number that essentially does the same thing. Tells you how much power is really doing something versus how much power is just getting sent back and forth in the wire. And so the last topic we're going to talk about in here is called power factor correction. And what that is that when you have some kind of a real load that you're putting on an AC circuit, usually those loads, because like machines that operate electrically are almost always based on electromagnetics, right? It's almost like either a relay or a motor or something like that is going to be based on there being a coil of wire that's doing something electromagnetic out there. So they're usually inductive, right? There's usually kind of an inductive profile to the different kinds of energy sinks that are out there that are accepting the energy. If you want to turn those more into just active power and less reactive power, it is typically possible for you to go and put a capacitor out there in parallel with that inductive load, and it helps you to deliver more or less, it allows you to make it so that more of your power that you're delivering is active power and that you have less reactive power going on in the same circuit. And that's going to be our last topic that we cover in here, is doing that power factor correction. We'll have our last test after that, and hopefully every single one of you passes the class. I'm looking forward to that. I want that to happen. So that's the course overview. Before I hang it up, anyone have questions that you'd like me to go back to in this list of ideas that I threw up here? You excited? Looks like it's going to be fun, right? I think so too.